Yes, very good morning to Unandal. Am I audible?
Yes, sir, you're audible, sir.
Yes. My screen are visible?
Yes, sir. MS Teams screen now.
Yes. Yes, in the past few days, what we have seen, we have introduced the robot motion analysis and control, and that is the the introduction of manipulator kinematics, the position representation, and in that we have seen the forward kinematics and reverse kinematics, that is inverse kinematics. And we have seen the 2 degrees of freedom arm, the forward transformation, that too with the forward transformation, and the reverse transformation, and then we have seen the orientation of three-dimensional degrees of freedom in yes, forward transformation of three-dimensional degrees of freedom arm, and then we have seen 4 degrees of freedom manipulated in 3 dimension, and then we have seen the homogeneous transformations and the robot kinematics, and we have solved a few problems in that topic. And during that time we have revealed about the transformation matrix, translation transformation, and rotational transformation matrix and all. This is the problem what we have seen yesterday. With this problem we concluded the yesterday's session. Yes. Okay, today we'll see about the kinematic equation using homogeneous transformation, and there are plenty of variety of authors revealed variety of information related to this kinematic equation. One among the renowned author is DH, that is uh, Denavit and Hartenberg, and based on his convention, we are going to reveal this information. And there are four vectors we are going to define in order to understand the end of n manipulator, and in order to understand the position and orientation, there are four vectors are used. See, this is the vector p vector, which is referred from the base, and we have three different axes, x1 and x, y, and z. N, A, and O. These are three terms we were introduced yesterday. That is the position of the end of the arm with respect to base frame. N, O, A are the representation of orientation of the end effectors. A is an approach vector, O is an orientation vector, N is an normal vector. Normal with respect to A and O. The four parameters what DH convention revealed, like length, twist angle, offset distance. These are the things we have introduced yesterday. And why we need to consider the rotation Z at first, and translation transformation matrix with respect to Z in the second, and why we are considering the translation transformation matrix the third, and why we are considering the rotational transformation in x direction at the fourth. This is what we are going to have. This is what we are going to learn today, and with yes, this is where we have introduced why we need to take this matrix at first, second, and why these orders were followed. And see why we have followed this order, based on the arrangements we were followed this order. We need to consider, we need to take the movement from the, we need to take the reference as base. Therefore we were taken the base as a reference, and that is what this order occurs. Anyway, detailed video lectures are available for DH, that we'll see today. Before that, do you have any current affairs? Do you have any current affairs? Yes, I'll tell you. The name changed for the Sardar Patel Stadium. What was the name? New name of Sardar Patel Stadium?
Narendra Modi Stadium.
Yes.
And two ends are named as Ambani End and Adani End.
And see, I usually disseminate the content to students. Please be aware with the happenings which is happening in and around us. In today's headlines in Sun News, what they are revealing about the information which was revealed by our Prime Minister. There is no necessity of handling with these industry and all. Government, it is not a duty of the government like that. He is revealing. What was your opinion about it? And there, if time permits, we will reveal. Our Prime Minister says the running or handling with the industrial is not the concern of the government like that. He stated, and it has to be the content has to be debatable when time permits, or if feasible, you have a discussion over this issue. Already the government doesn't have involved in the education and the in medical. Now it is very transparent that government doesn't have any influence over the industrial and all. Where it will lead, we don't know. Be aware of these happenings and all. And on one side, in Hindu headlines, vaccines for seniors and 45 plus with commodities from March. That is the other headlines. On one side, the photograph, the cricket landmark photograph is available in the Hindu headline. On the other side, vaccines about the seniors. That was the information in Hindu. And okay, now we will reveal about the DH convention and what has happened in the stadium yesterday. I think third.
Day one of England, India was England third test.
India won.
No, sir. 13 wickets fell in day one. They were
Okay.
like 130 not all out, England.
Okay, 1 and 12. England.
Something like that. I don't remember exactly, but they got out 100 and
India
something.
finished 99 on the third day. Is it right?
Yes, sir. 99 for 3, sir.
Yes, yes, and we concerning the stadium, the largest world largest cricket arena, which can accommodate 1.1 lakh spectators. That was nice. That was nice, but the principle apart from these things has to be discussed. Okay, please have a visit of this video which reveals the information about DH convention. Please make a note. Please make a note of each and everything. It is audible. This content is audible.
Continuing with our study on
Yes, sir.
fluid kinematics, and we're going to introduce a powerful method for deriving this called the Denavit-Hartenberg parameters. So in the previous lecture,
You please make a note. You have your notebook and please make a note of each and everything.
That we can concatenate transformation matrices between joint frames to determine the end effector pose. So we can multiply all the transforms from frame 0 upward through our forwards kinematic chain to the end effector of the robot. And so this is just a product of all the transforms from joint J-1 to J. And we just need to describe this transform J-1 to J as a function of simple geometry. Okay, so Kismet has joined me here to help describe Denavit-Hartenberg parameters. So the Denavit-Hartenberg parameters are a really powerful tool for describing forward kinematics. And what this says is the transform between any two reference frames on a serial link chain can be described with a minimum number of 4 parameters. Right? So we have a minimum number of 4 parameters applied in sequence. We rotate about the z-axis by theta. So in our first transform, we have a rotation about z by theta. We translate about the z-axis by d. So in our second transform, we replace the z component with the variable d in the translation.
First, we are concerned about the rotational transformation, and second, we are concerned about the translation transformation. And accordingly, we need to take the order sequence.
Vector. The third one, we translate across x by variable a. So in our third transform, the x translation component is given by a. And then lastly, we rotate about the x-axis by alpha. So in our last transform, we have rotation about x by.
These symbols have it is a little word little different than the groover. Anyway, the content are very good. You please make a note.
Angle alpha. So for our joint frame j-1 to j, we have the concatenation of all these transforms. So first a rotation about z by theta, a translation about z by d, a translation about x by a, and a rotation about x by alpha.
Yes, from the base we have given the uh, uh, arrange the equations. That is why we were discussed in the arrangements of equations. See, rotation in z direction and translation transformation in the z, translation transformation in x, and then rotational transformation in the x direction.
And therefore, to get the forward kinematics from frame 0 to frame n, then we just multiply all of these together. So we have j-1 to j for every joint j up to n joints, and we multiply all of these together. So here is a nice little animation.
How we can read this the end effector frame t when the joint is concerned about 0 and n, then the summation of j is equal to I to n t ij minus 1 to j.
Showing what it looks like. We rotate about z, translate about z, translate about x, and then rotate about x. So why do we use the DH parameters? Well, firstly, it's the minimum number of parameters needed to describe forward kinematics. So we could define any kind of transformation matrix between frames, but DH parameters are the most efficient. It also allows us to use universal nomenclature. So knowing the DH parameters gives complete knowledge of the kinematics of a robot. And also it's easily understood by anyone. And then it's also computationally efficient for the differential kinematics and dynamics. So we need to minimize the number of calculations for high frequency feedback control. So even though we have super powerful computers, this can still add up, especially when we have lots of sensors, lots of vision processing, really complex robot structures. We really need to minimize the computational cost for our robot control.
It is audible. It is audible. Something went wrong. Yes. Yes, it is audible.
Yes, sir.
Yes, simulation. Okay. If there isn't any interruptions, you please remind me. Huh? We have net issues. If you have any issues, you are unable to get the audio or video. If something went wrong, please remind me.
Sir, it's not audible.
It is not audible, ah?
No, sir.
Yes, I'll just a minute. I'll again share. Pradeep, full போயிடுச்சா? அப்படியே எங்க வருது ஒன்னும். ஆ. Now check with the audio.
Zj minus 1 is perpendicular form. We replace the for a. So there are rules
Yes, sir, audible.
Yes.
for applying DH parameters. The first is that we actuate about the z-axis. So for a revolute joint, we just rotate about z like shown. So in our first transform, if we have a revolute joint, we replace theta with q. And if we have a prismatic joint, we translate about z. So our second transform, we replace the z component with q. Right? So we only actuate about z.
See, this is for revolute joint and this is for prismatic joint. Even there might be a chance for doing the translation transformation in the revolute joint, but in the case of prismatic joint, we doesn't have any. There won't be any chance for the rotary motion.
Second, the axis for Zj minus 1 is perpendicular to and intersects the axis for x of frame J. So as you can see in the diagram here, these two axes projected will intersect and they're at 90 degrees to each other. Lastly, we don't need to define the y-axis. This is just solved implicitly. So the y-axis will just be the cross product of z and x. Right, so here are some tips for DH parameters. Firstly, the joint frame does not need to physically coincide with the actual joint. It only needs to align with the axis of actuation. So in this depiction here, we can see that the physical joint might be up here, but the frame of reference for this joint can be anywhere along this axis. Right? It could be anywhere here. It doesn't need to be on the actual joint. Second, the robot arm can be arranged in any configuration that suits the DH parameters. So the robot configuration should suit the DH parameters, not the other way around. So we can put this joint here in any location around its previous joint, but we just pick the one that suits the DH parameter configuration, and that would be in this location here. Right, so to get a forward kinematics at a particular joint configuration Q, we just substitute the joint value in the Z component of the transformation chain. So the transform from frame J minus 1 to J, if we have a revolute joint, we just substitute the rotation about Z with the joint variable Q here. And for a prismatic joint, we substitute the translation component about Z with our joint variable Q. Now, alternative sequences can be used for DH parameters, and this is one that I made up, so it might be not 100% accurate, but it illustrates the point. So I had D, theta, alpha, A. But the important point is that we must use the same sequence. Matrices are not commutative, and so use the same sequence for all joints. So different textbooks will give different combinations of DH parameters. You must use the same one and specify which ones you have used. So let's return to our 3-DOF manipulator that we looked at for the forward kinematics in the previous lecture. So the DH parameters from frame 0 to 1 is first given by a rotation about the z-axis by Q1. So this is our variable Q1 for this joint, and we're rotating about the z-axis. So our first transform will be given by this matrix here. And then we want to move up the z-axis. So to get to the next frame, we have to move up by L1, the distance of this link length here. Then the next one will be a translation about x by a. But you can see that there is no offset between these joints, and so a will be 0. And lastly, we have to rotate about the x-axis by alpha. So to get this z-axis here to align with this z-axis here, we rotate about x by pi on 2. Now, we want to get from frame 1 to 2. So again, we have a revolute joint and we rotate about the z-axis. So this is our variable q2 about the z-axis z1. So we just substitute q2 into a z rotation matrix. Then the next would be a translation about the z-axis, but you can see that these are not offset in z. So therefore, we have 0. Then we have a translation about x. So to get from here to here, we translate by the link length L2. Then the last would be a rotation about x by alpha, but you can see that these two frames are already in alignment. And so therefore, we have 0 rotation, which will give the identity matrix. Then lastly, we go from frame 2 to 3. And so again, we rotate about z here, q3, and therefore we substitute q3 as our variable theta. We translate across the z-axis by d3, but again, because these are not offset in z, therefore this is 0. The next will be a translation across x by a, and so we have to move along the x-axis, and this is just the link length L3 for the x component. And then lastly will be a rotation by alpha about the x-axis, but again, these frames are already in alignment, so this alpha will be 0, which gives the identity matrix for a rotation about 0. Right, so therefore we have solved all the transforms from j-1 to j of our 3-link manipulator. So let's consider this 3-DOF manipulator with a prismatic joint. So from frame 0 to 1, it's the same. We have rotation about the z-axis by q1, translation up z by L1. We don't need to translate about x, so this will be a 0. And then we have to rotate by pi on 2 to get the 2 frames in alignment. And note that for this case, frame 2 is coincident with frame 1. So we had before I described that the frame of reference for a joint does not need to be located on the physical axis, and therefore to perform the DH parameters on this type of structure, the frame for this joint here must be located down here, coincident. Otherwise, the DH parameters won't work. And this is fine. It still works out mathematically. So 1 to 2, so we're at frame 1 and we're going to frame 2, and they're in the same location. Again, Q2 about Z1. They are coincident, so we have no translation about Z and no translation about X. But now we need to rotate back by pi on 2 to get this Z-axis pointing up. So negative pi on 2 to cancel out this pi on 2 here. And since frame 2 is not located on joint 3, right, so this frame is not up here where the physical origin of the joint would be, we need to add the link offset for the Z translation. So we start with a rotation about Z, but we don't need to rotate about Z, so this will be 0. And we translate across Z by L2 plus Q3 to get from here to here, or more importantly, here to here. And then we don't need to move about the x-axis because they're in alignment, so that's 0. And again, we don't need to rotate about x anymore either because these frames are now oriented in the same way. So this will be 0. So this would be an example of how to perform the forward kinematics with DH parameters where we have some sort of annoying kinematic structure like so. So therefore, frame 1 and 2 are coincident, and we account for this offset between frames with our DH parameters here. So I'm going to give you some common joint-to-joint transforms that I have seen in my limited experience. So the first would be exactly what we saw in the previous example. So we have joint frames that are coincident. So when these two joints are perpendicular, we need to specify this joint frame down here at the same point as the previous one, J minus 1. And therefore we have a rotation about Z by Q, no translations at all, and we just do a plus minus pi onto to get the Z axis of J pointing up. The next would be this kind of arrangement. So we have Z rotation with Q, translation up Z by the link length here, no translation about X because they're in alignment, and then we have to rotate about pi onto to get the Z axis pointing this way, which is orthogonal to this one. And lastly, this really simple arrangement. So again, a rotation.
When we are applying a negative pi by 2 and when we are applying a positive pi by 2. Here the result rotational transformation occurs at the same point, and this distance given for our understanding, but here there is a translation motion with a amount of Lj, and here we are applying minus pi by 2, and the second case we are applying a positive pi by 2, where we are applying a negative and where we are applying a positive pi by 2. Morning still all are sleeping, huh?
Direction of the sir, I think when it is in the positive direction of x-axis.
Yes, Kumar Hartik. Yes, go ahead. See, when we are we need to take it negative, and when we need to consider positive in the pi by 2.
Yes, sir. I was saying when we need to get the axis coincident in the direction of any of the positive direction of axes, like for positive x-axis, we need to get that in a line. We go for plus pi by 2, and similarly, I guess minus pi by 2 if we need to get that in negative direction.
Yes, yes, yes. Very good.
About the z-axis by q. We have no offset in the z-axis, so this is 0. We translate across x by the link length L here, and then again, because these frames have the same orientation, we don't need to rotate about x, so that's 0. Right, so let's summarize what we learned about DH parameters. The forward kinematics can be calculated by multiplying transforms between joint frames. So to get the transform from frame 0, usually the base frame, to frame n, the end effector of the robot, we just multiply all the individual transforms between joints. The DH parameters give a minimum number of 4 parameters applied in the same sequence to get the transform from frame j-1 to frame j. So for a revolute joint, we replace the rotation about z with our joint variable q. For a prismatic joint, we replace the translation about z with our joint variable q. And again, these transforms must be applied in sequence, and the individual parameters within this sequence are first a rotation about z by theta, a translation about z by d, then third, a translation about x by a, and lastly, we rotate about x by alpha.
Yes, yes. Do you have any doubts with this presentation? Do you have any doubts with the past presentation? This is the order which we have followed based on the DH convention. Yes, go ahead. Yes.
Sir, can you put this video link in the chat box, sir?
Sure. Yes, I'll upload in our YouTube. In Google Classroom, you can find.
Thank you, sir.
Yes, find the one more DH representation.
Hi everyone. In this video, which is the second video for the direct kinematics section on robotics, we will be looking at the Denavit-Hartenberg or the DH representation. Now in my previous video, we discussed assigning frames for a robot manipulator. If you're not quite familiar on that, check it out by clicking the link up here. In this video, we will be using those frames to create a DH table, and from that, later on, a transformation matrix when moving from one frame to another. Without waiting any longer, let's get into it. Don't forget to like these videos, give me a thumbs up, and click that subscribe button. I'm Chums, and welcome to That's Engineering. Alright guys, so before we look at DH tables, let's have a look at our link joint parameters, the 4 values which make up our DH tables. Now these can be understood by considering 2 arbitrary joints. So let's just imagine a joint here, a revolute joint, connected through some sort of link to another revolute joint over here. Now each of these joints would have their joint axes. Right, so the first value is our AI minus 1, which is the link length. For this, it would be the length of the common perpendicular between both these two axes. So that would be your AI minus 1. Your second parameter would be the link twist. So if we assume this joint to be our ith joint, this would be our I minus 1. So this axis can be redrawn over here, sort of something like that. And this angle would be our link twist alpha I minus 1. The third value is the link offset, which is the offset distance between the link and the common axis. So sort of something like this. And theta I would be the rotation of the joint. So typically DI values will only exist for prismatic joints because they move linearly up or down, left or right, while theta I values will usually exist only for revolute joints as they revolve around a particular axis, which means revolute joints should have a 0 DI, while prismatic values should have a 0 theta I. So these are the 4 definitions that we will be using to find these 4 parameters. It is best to keep these definitions in mind and understand them, as it would make problem solving much easier. If you look at these definitions, like I mentioned earlier, only two axes are needed, the z-axis and the x-axis. In this case, for example, zi would refer to the axis under question, while zi plus 1 would refer to the next joint axis, and zi minus 1 would refer to the previous joint axis. Using these four values, we can form a DH table or a Denavit-Hartenberg table. And using the values in the DH table, we can later find our transformation matrices. Using a particular equation. Now, using these definitions are best understood through an example. So let's have a look at it. So, looking at this example, we assigned the frames in the previous video. You can see there are three joints. You have a prismatic joint, a revolute joint, and another revolute joint. So just by looking at the diagram, you should be able to tell that the prismatic joint should have some value for di, and that would actually be given by this variable here, d1. The two revolute joints should have some value for theta, which would be theta2 and theta3. The frame for the tool was already given in the question, while the base frame was assigned in relation to the first frame. Now this would be our DH table, and the first step would be to identify the axes. So we have three axes, 1, 2, 3, corresponding to our three joints. However, when setting the parameters for the DH table, we would always move from one frame to another. So in the first case, we will move from 0 to 1, then from 1 to 2, and 2 to 3. So let's consider the first case, moving from 0 to 1. Now for the first two parameters, a and alpha I minus 1, I would be equal to 0 because our zi would be 0 and zi plus 1 would be 1. But in the case of di and theta I would be 1. So our xi minus 1 can be 0 and our xi can be 1. This is because we want to keep our xi's and zi's in relation. So let's have a look at it. For ai minus 1, we want the distance from z0 to z1 about our x0. So the distance between our z0 and our z1 along x0, and you would see that this value is actually 0 because z0 and z1 are in line with each other, and so there is no displacement along the x-axis. The second value, alpha I minus 1, looks at the angle between z0 and z1 about x0. So this is the angle z0 has to rotate to align with z1 about x0 axis. And as they are both pointing vertically upwards and in line, this angle is 0. Now I becomes equal to 1. Again, we want the distance for di between our x0 to x1 about z1. So the distance between my x0 and x1 about z1 would actually be d1 because it is a prismatic joint. Whereas the angle from x0 to x1 about z1 would be 0. And this is because x0 and x1. So how we can rotate our x0 to match up with x1 about z1. So the rotation will be here. They're both in line and both point.
Based on the past video, what would be the order of these four different columns? We have a I minus 1, alpha I minus 1, di and theta I. We can rearrange this four column as per our wish. Based on the past video, what would be the orders? Yes, someone unmuted. Yes, go ahead. di theta I a I minus 1 and alpha I minus 1. That might be the order di theta I a I minus 1 alpha I minus 1. And you please go ahead with these 1 to 2, the link 1 to 2, 2 to 3. Someone please unmute your mic and tell me what will happen for this 4 different unknowns when we are concerning about link 1 to 2 and 2 to 3. See here 1 2 3 and there is an here we have translation transformation. It doesn't have any rotational transformation. Yes, tell me what happened.
Pointing in the same direction, so the angle would be 0. There would be no rotation around Z1. Now let's look at frame 1 to 2. Right. So now considering frame 1 to 2. So for the first two values, our I would be equal to 1. So our AI minus 1 would want our distance from Z1 to Z2 about x1. The distance between Z1 and Z2 in the direction of x1, and this would actually be the length of the link from Z1 to Z2. So we can imagine a parameter or the length of the link to be L1, and that would be your AI minus 1. Then the angle between Z1 and Z2 about x1. So this is the angle Z1 must rotate to match up to Z2 if rotated about x1's axis. As both Z1 and Z2 are parallel and pointing in the same direction, this angle is 0. Now we look at I equals 2 for the final two parameters. For di, we want the distance between my x1 to x2 about z2. The distance between my x1 and x2 in line of z2. So x1 and x2 are both on the same plane. There is no vertical displacement. So this is 0. For theta I, the angle between x1 and x2 about z2. So the angle x2 rotates away from x1 about z2, and this angle would be theta 2. So as you can see, this is a revolute joint. Hence, it has a 0 di but a theta value. While as previously we were looking at a prismatic joint, so it has some di value, which is d1, but a 0 theta I value. Now you can repeat these steps for axis 2 and 3, and if you do so, you should get L2, where L2 is the link length from 2 to 3. Alpha I minus 1 should be 0, di should be 0, it's a revolute joint, and so theta I should be theta 3. Sorry, theta 3. So that's how you assign the values to the DH table while considering the frames of the robot. Alright guys, so that's all for this video. If you guys liked it, please give me a thumbs up by clicking the like button below.
Yes. Do you have any doubts? Do you have any doubts?
Sir, the last value of rotating x1 about x2 about sorry x1 to x2 about z axis. How are we getting that theta 2 and theta?
See how we are getting theta 1. There isn't here. There won't be any changes with this diagram, but there is a possibility with the rotary rotation at the axis z2. Here see theta 2 and theta 3 we have the revelatory joint. Therefore, we need to assign theta 2 at theta I, and similarly theta 3 in the case of the other link. Okay.
Sir, but it is the angle from x I minus 1 to xi above zi. So, like, I'm not understanding how this is.
No, see here. Here you please take this Z2 little far away from the actual axis towards right, and this might be towards left. And what happens when theta given we were given some value for this theta, then only we can able to see the changes with this link. Similarly, for this link, when we are applying there is in theta, at that time only we can able to see, we can find some changes with the end effector. But here, these three lines are parallel. X1, X2, and X3 are parallel. That is why you're not able to understand. See here, this link is slightly towards right, and this would be left. What happens when there is an inclination with the theta? There might be a chances for this inclination. And similarly, if we can do the changes with this joint, then only the end effector we can move with. There is a possibility of inclination with these. This is the way that we can make the changes with the end effector. Okay, it is. Are you getting the point?
Yes, sir. Like, this can be 0 to, it depends on the theta value given in the question.
Yes. At present, the theta 2 and theta 3 is 0. At present,
Okay.
Yes. Yes. Oh, that is why we were arranged the AN in this sequence. That is rotational transformation and translation. Do you have any doubts?
Sir, you are not able uh, for the past few minutes, sir.
Yes, of course. Network issue. Do you have any doubts with the videos?
No, sir.
Okay. If you don't have any other doubts, we'll close the session, and